Hello, everyone. We are back for Chem 65, Chapter 4. The topics discussed in Chapter 4 are going to be chemical reactions and equations. Broadly speaking, the contents of this lecture we'll look at the chemical equation, types of chemical reactions. We will look at molecular, ionic, and net ionic equations. We will look at some types of reactions, including composition, decomposition, combustion reactions. We'll look at neutralization reactions and titrations, and then finally, I'll look at redox reactions. So without further ado, let's get going. So because this chapter is about chemical reactions, I wanted to repeat something I believe is in a previous chapter. So just looking at atomic theory. So when we balance equations, we're going to obey conservation of mass. So just to remind each other, we have the law of conservation of mass discovered in the late 18th century by Antoine Lavoisier. So we know that mass is always conserved during a chemical change. The reactant mass equals the product mass. It might be hard to count, but they should be equal. We know the law of constant composition from Joseph Proust, again in the late 18th century. Atoms can rearrange in different whole number ratios, but if the same elements come together in the same ratio, they form the same compound, and compounds have this predictable ratio of elements. And then John Dalton realized the law of multiple proportions. So you take the same elements, so in this example nitrogen and oxygen, they come together in different ratios. You can get a multiple of definite proportions or a multiple proportions. Okay, so this is some of the background on basically some of the rules on how to rearrange atoms, what happens when you do it. And we're going to build on this when we look at chemical processes, chemical reactions. We've previously seen that Dalton's atomic theory, although not completely true by today's standards, roughly says that when you divide materials down to the building blocks and you can't divide any further, we call those things atoms, or these indivisible units of matter. He said that all atoms of an element are identical, although we know of the existence of isotopes today. Dalton didn't know about isotopes, so we know it's not quite correct by today's standards. Atoms of different elements are chemically different. Yes. So for example, helium is chemically different than hydrogen, is chemically different than oxygen. And that's because of the different numbers of subatomic particles that go into the different elements. And then atoms can combine in integer ratios to form compounds. Yes, this builds on Joseph Proust's definite proportions. And then finally, chemical reactions involve a rearrangement of atoms, not a change in the atoms themselves. Yes, this goes back to the idea that matter is not divisible. So this was again, a review of Dalton's atomic theory, so that we've laid the foundation ready for chemical reactions. Okay, so a chemical reaction is a way that a chemist can present a change in materials with time. We have the reactants on the left. So anything to the left of an arrow is a reactant. That's what exists initially. Anything to the right is a product. That's what exists finally. And we have this shorthand way of doing it with coefficients and what have you. So for example, this coefficient 2, let me get my pointer. This coefficient 2 means I have 2 hydrogen molecules as gases. So this is what they would look like. I've got 2 hydrogen molecules, and then I've got an oxygen molecule. If there's no number, we assume the number is 1. So 1 oxygen molecule shown here. It's also a gas. And over time, this produces 2 water molecules, which are liquids, L. So we have these 2 structures of water molecules over here. When we balance a chemical equation, the idea is to make the mass of reactants and products the same. So because the mass of each element is the same, then we just have to count the total number of types of element on either side. Once we have chemicals that exist, all we can do then is add coefficients. We can't add subscripts, for example. So for example, in this problem, if we ignore the coefficients for a second, we see that I have 2 hydrogen as products, but I only had as a chemical 1 hydrogen as a reactant. So I had to go and multiply the hydrogen on the left by a coefficient. Why not 2? Well, ultimately it became 6 because I had to multiply chlorine as well. So if we inspect now, so there's some iteration that is hard to show in these static slides. But if we count now, we have 6 hydrogens on the left. 3 multiplies the 2, we have 6 hydrogens on the right. We have 2 aluminum on the left. The 2 multiplies the aluminum, we have 2 aluminum on the right. The 2 also multiplies the chloride, so we have 6 chloride on the right, and that's matched by the 6 chloride on the left. So there's no way of changing these coefficients to make them balanced and not have a fraction. So again, it's an iterative process, and my students will have some homework to practice this. Okay, consider the following balanced chemical equation. So we have 2 lots of C2H2 and 5 lots of oxygen to give 4 lots of CO2 and 2 lots of water. So we're starting to look at conserved quantities, which eventually will develop into the mole, but not quite yet. The goal here is to know how many CO2 molecules are formed when 26 molecules of C2H2 are reacted. Okay, so I've got my balanced chemical equation. What does it mean? It means I can set anything in the balanced chemical equation equal to anything else. So I could say that 2 lots of C2H2 are equal to 5 lots of O2, are equal to 4 lots of CO2, are equal to 2 lots of H2O. In this case, I'm interested in counting CO2. So I reverse construct this. So I've got CO2 equals CO2. From my balanced chemical equation, highlighted here in blue, I have 4 lots of CO2 are equal to 2 lots of C2H2. My denominator C2H2, I can now write as a preceding numerator, and it will cancel. So the only unit that is left is just multiples of CO2. So I multiply 26 by 4 divided by 2, and I get 52 lots of CO2. So this is an example of what I can do once I've balanced the chemical equation. Okay, let's look at types of chemical reactions. We can have combination reactions, literally where small chemicals are combined together to make more complicated and larger chemicals. We can also call these synthesis or composition. Here's some examples shown in the gray box here. So we've got 3 lots of hydrogen and 1 lot of nitrogen to give 2 lots of ammonia. So we can see that we've combined these elements together to make something more complicated. Second example, we have magnesium oxide and carbon dioxide to give magnesium carbonate. Again, we're taking compounds, bringing them together to make something more complicated. And the other 2 examples are further examples of where the reactants are more simple, the products are more complicated. So they would be combination reactions. Decomposition is the opposite of combination. So our reactants should be more complicated than the products. So for example, we have this iron 3 hydroxide species here. We heat it up and we make iron 3 oxide and water. We can take water and electrically decompose it to give its elements, hydrogen and oxygen. We can take silver bromide and add photons of light to make silver and bromine. And then finally, carbonic acid will decompose to give carbon dioxide and water. So again, these should look to you like the reverse of synthesis. Okay, combustion is a different type of reaction. We always have molecular oxygen as one of the reactants in combustion. The other reactant is a fuel. Here, the fuel all contains carbon, but that's not always the case. And with combustion, we want to add molecular oxygen to each element except oxygen in the fuel. So if the fuel is just carbon, we add oxygen to carbon to make CO2. If the fuel is propane, which contains carbon and hydrogen, we add oxygen to carbon to make CO2. We add oxygen to hydrogen to make water. Methanol contains carbon, hydrogen, and oxygen. We add oxygen to carbon to make CO2. We add oxygen to hydrogen to make water. We don't add oxygen to itself. And the same goes for acetone. So essentially, whenever you have carbon in your fuel, you're going to form, and it's complete combustion, it's going to form CO2. If it were incomplete combustion, you might form other things like carbon monoxide, CO, or just regular carbon, which is just C. Any hydrogen will combine with oxygen to form water. Another type of chemical reaction are double displacement reactions. The general template for double displacement is shown here in red. So we have two ionic compounds, AB and CD. They exchange partners. So A now exchanges with C to form a compound with D, and C exchanges with A to form a compound with B. So it's called double displacement or double replacement because we have two ionic compounds that displace or replace each other. Examples are given in the gray box. So we can have potassium bromide and silver nitrate. The potassium takes nitrate to make potassium nitrate. The silver takes bromide to make silver bromide. Here, the arrow just means a precipitate is formed, but more about that in a few minutes. Again, sodium sulfate, the sodium takes chloride to make sodium chloride. The strontium takes sulfate to make strontium sulfate. And the other two examples can be followed in a similar manner. A relative of double displacement reactions are single displacement reactions. The general template for a single displacement reaction is shown in red. So we can have an element A plus an ionic compound CD. A will displace C to form the compound AD, and then C will have been ejected and will have no one to partner with, so we just get elemental C. Examples of single displacement are potassium and water. The potassium displaces the H to form potassium hydroxide, and the H is left to partner with itself to make hydrogen gas. Magnesium reacts with copper 2 nitrate. Magnesium displaces copper to form magnesium nitrate. Copper is left alone as metallic copper. The other two examples follow a similar pattern. Oh, one other thing we should probably mention about single displacements that will become relevant in a few minutes is single displacement reactions are always redox reactions. So more about that in a few minutes. Okay, and here's a few minutes. Let's look at redox reactions. With redox reactions, we're interested in electrons being exchanged between species. So an oxidation state is a way that we can assign the relative, I guess, post-exchange of electrons. We can assign each element in a compound an oxidation state. In a way, the oxidation state reflects the mood of the element, and it's a good idea that chemists not only know the oxidation state to know what mood the elements are in. You know, extreme oxidation states can be a source of chemical reactivity, for example. But also, if we assign oxidation states to elements, we can look for evidence of redox, because oxidation states must change for there to be redox. So there's some rules that we need to know. Firstly, the oxidation state of any element, whether it be in a solid, liquid, or a gas, or whether it be in a cluster of its own kind. So for example, Cl2 is clustered with itself, S8 is clustered with itself. If it's one type of element by itself, regardless of what state it's in, solid, liquid, or gas, the oxidation state is 0. If you have a monatomic ion, the oxidation state is numerically equal to the charge. That doesn't mean the oxidation state is the charge. That means the oxidation state is numerically equal to the charge. Just a note on syntax, whereas the charge, for example, in a magnesium cation is 2+, and we have a superscript where the number comes before the sign plus. If we report the oxidation state, there are no superscripts, it's just regular syntax, and we have the plus before the 2. So a magnesium cation +2 charge, 2+ charge, has an oxidation state of +2. Polyatomic ions, we have to solve for the oxidation state of the weakest element present, and more about that in a few minutes. When we try to assign oxidation states in polyatomic ions, we always assign preference to the most electronegative atom. Electronegativity is a type of strength of an atom, and looking at the periodic table, the elements in the top right of the periodic table are strongest, the elements in the bottom left are weakest, and strength differs on that diagonal. So for example, fluorine is in the top right, preferentially forms a -1 charge. We prioritize fluorine with a -1 oxidation state. Oxygen is also in the top right of the periodic table. -2 charge is its preferred charge. So we assign it preferentially a -2 oxidation state. Okay, other things shown in this box here. We want to be able to look for redox agents. So there's an acronym we can use when we look for evidence of redox, and the acronym is OILRIG. So OIL, O-I-L, is an acronym for oxidation involves loss of electrons. RIG, R-I-G, is an acronym for reduction involves gain of electrons. So OILRIG. Oxidation is when you have an increase in oxidation state, or you have electrons as a product, or you lose electrons. They all say the same thing. Reduction is when you gain electrons, or you have electrons as a reactant, or you decrease the oxidation state. Those three things all mean the same thing. Reducing agents undergo oxidation. So once you have your oxidation reaction, the reactant in the oxidation reaction is the reducing agent. Oxidizing agents undergo reduction. So when you have your reducing reagent, when you have your reduction reaction, so many words, when you have your reduction reaction, the reactant in your reduction reaction is the oxidizing agent. Okay, here's some examples. So we have this polyatomic ion here, this bicarbonate ion, HCO3-. So it's a polyatomic ion that has a total charge of -1, and it's made of hydrogen, carbon, and oxygen. So we set the whole thing to -1, and we know that we have oxygen is the most electronegative, so we prioritize it. We have 3 oxygens, so we have 3 multiples of -2, where -2 is the charge on oxygen. We have 1 carbon, and carbon here we've called X. It can vary. Hydrogen is typically always +1, so we'll just assign +1 to hydrogen, and we have 1 of them. So we have a little puzzle here where we have to solve for X. So we can see here by applying some algebra, X equals +4. So now we know the oxidation state of each element in bicarbonate ion is +1 for hydrogen, -2 for oxygen, +4 for carbon. Here we have calcium cyanide. We know that calcium is a group 2 metal. Not preferential. The charge on a group 2 metal cation is +2, so that becomes a +2 oxidation state for calcium. Then we solve for the polyatomic ion cyanide. So cyanide has a -1 charge. So I can write it, maybe I'll try and annotate over this a little bit. So we can say that cyanide has a -1 charge. And I've got carbon and nitrogen. Well, nitrogen, there's only 1 of them, and nitrogen preferentially forms a -3 charge. Carbon, we're going to solve for carbon in this case. So again, I'm looking at cyanide, which is Cn-, and that's the source of my -1 charge. Okay, so I've got X -3 is -1. If I take the X over, sorry, if I take the -3 over here, it becomes plus. So X equals -1 + 3, which is +2. So that's where this +2 comes from. So again, oxidation states for the 3 elements in calcium cyanide are +2 for calcium, -3 for nitrogen, +2 for carbon. What's this? Iron 2 phosphide is our final chemical over here. Again, iron is a transition metal. It can have a variable charge, so we have to solve for it. But we know the phosphorus preferentially is -3. And I have 2 of them, so 2 -3s on -6, and then 3 multiples of whatever ion is, let's call it X, adds to this -6 to give me a neutral compound. So if we do some algebra, we solve that X must equal +2. So we have the oxidation state +2 for iron. Okay, let's move now to some labels. Strong and weak. So when we talk about strong in chemistry, we mean completely dissociates. So any species that will completely dissociate and form free ions with 100% extent is called a strong electrolyte. Here, electrolyte just means ion. Examples of strong acids are HCl, HBr, HI, HNO3, HClO4, H2SO4, but only the first hydrogen. So when we have strong acids, although they separate into H plus the anion, H is not stable. It will immediately interact with a water molecule to make H3O+. Strong bases, on the other hand, are any group 1 or group 2 hydroxides. So group 1 here are the alkali metals, group 2 are the alkaline earth metals. So these are not an exhaustive list, but these are worth knowing by heart. On the other hand, weak electrolytes are any species that partially dissociate, and by partially we mean less than 50%. So they predominantly exist as molecules rather than free ions. So even though they can form ions to a limited extent, we represent them as molecules. Non-electrolytes are compounds that do not dissociate at all. And typically in Chem 65 or an introductory course like this, there are some basic solubility rules that you can learn, but for the most part, you'd be assigned a solubility chart because solubility can get pretty complicated. Okay, principal species. In the following discussion, this is my handwritten scribbles. In the following discussion, AQ, which stands for aqueous, just means dissolved in water. So for example, we know that nitric acid is a strong acid. We put it in water, it will completely dissociate into its ions, hydronium and nitrate with 100%. So no HNO3 remains at the end of this process. It's now 100% H3O plus and NO3 minus. Therefore, when we write nitric acid in its principal species form, we don't write HNO3, we write H3O plus NO3 minus. Weak acids, on the other hand, for example, cyanic acid, HCN, is a weak acid, and so its principal species is molecular. We just write it exactly the same. So HCN. We don't write it as H3O plus CN minus. Why? Because it's not a strong acid, it's a weak acid. Clean my glasses a bit. Other examples of principal species, we have perchloric acid, HClO4. It's strong, so we write it as H3O plus and ClO4 minus. Lithium hydroxide is a strong base. We write it as free ions as Li plus, aqueous, OH minus aqueous. Barium hydroxide is a strong base. We write it as Ba2 plus aqueous, 2OH minus aqueous. H2S, hydrosulfuric acid, is a weak acid, so we write it as a molecule, H2S. Acetic acid is a weak acid. We write it as CH3COOH. And formic acid is also a weak acid. We write it as HCOOH. So again, depending on whether you're weak or strong, depends on how we write you in your principal species form. Okay, this becomes relevant. These principal species become relevant now when we start to talk about precipitation reactions and what have you. Okay, a precipitate can either be a solid, liquid, or a gas, where there was not a solid, liquid, or a gas on the reactant side. So the precipitate has to be a product. One way that we can predict products and then check them in a solubility chart is to use an example here shown as the probability square. So for example, if we were going to react zinc nitrate together with potassium phosphate, we could write zinc nitrate as a column. We could write potassium phosphate as a row. And then the diagonal we ignore because cations don't interact and anions don't interact. But when we exchange partners in a double displacement, the zinc is now going to take the phosphate to make zinc phosphate. The potassium is going to take the nitrate to make potassium nitrate. And we can check the solubility of these products in a solubility chart. We realize that zinc phosphate is a solid, therefore we have a precipitate, and this is evidence of a chemical change. This is a driving force behind the reaction. And without, for example, a precipitate or something else like a color change or a gas produced, we really have no evidence of any chemical reaction. But more about that in a couple of minutes. We're going to split writing chemical equations up into 3 different forms, and the utility of doing this hopefully will be revealed as we do it. So far, we've looked at molecular equations. So A molecular equation is just writing everything as a molecule and balancing it. So in this example, we have iron 3 chlorate and sodium sulfide to give iron 3 sulfide and sodium chlorate. That would be a molecular equation, and it's completely balanced. If we wanted to write the complete ionic equation, we would separate any aqueous species, only aqueous species, and only separate them if they are strong electrolytes. So if they're aqueous but weak electrolytes, we don't separate them. So iron 3 chlorate is a strong electrolyte, so we separate it into 2 iron 3s and 6 chlorates. Sodium sulfide is a strong electrolyte, so we separate it into sodium ions and sulfide ions. We don't separate solids, so we just rewrite iron 3 sulfide. And sodium chlorate is a strong electrolyte, so we separate it into sodium ions and chlorate ions. To get the net ionic equation, we cancel spectators. Spectator ions are anything that's common to the reactant and product side. So as we can see, chlorate is common to both sides. We can see that chlorate is present as a reactant and product. And I'm going to not be able to erase that now. Yes, for some reason, now and again when I try and annotate like that, it won't let me do it. All right, I'm gonna have these black marks stuck on the page now. So I can cancel chlorate on both sides. I can cancel sodium on both sides because it's common. And what I'm left with is iron sulfide and product iron 3 sulfide. So I write that as a net ionic equation as shown. The utility of doing this is, whereas initially it looks like I have 2 products in the molecular equation, in reality, sodium chlorate is not a product. It's a collection of ions floating around freely. So my only product in the molecular equation is actually iron 3 sulfide. And that's exemplified by writing a net ionic equation. Okay, let's look at neutralization reactions. A neutralization is when you take an acid and a base, you neutralize it to form a salt and water. Now, this doesn't mean you have a neutral pH or anything like that. It just means you've neutralized the original acid and base. You might still have a slightly acidic or basic salt, but you tend towards neutrality. An example, we have oxalic acid and sodium hydroxide to give a water and sodium oxalate. Let's see. Exceptions to this rule are if we have a base that contains carbonates or bicarbonates. In these cases, they would both decompose to give carbon dioxide and water. If we have sulfites or bisulfites, these can decompose to give sulfur dioxide and water. If we have sulfides, we could get hydrogen sulfide gas. And if we have ammonium ions in our acid, then this can decompose to give ammonia and water. So these are some exceptions. These will become obvious if we treat neutralization reactions as double displacement reactions, which they are. It all becomes straightforward. Okay, normality. Normality is an older but definitely useful way to monitor an acid-base reaction because we can make a sweeping statement about normality. And it's down here in blue. Acids and bases always react in a 1-to-1 equivalent ratio. So normality measures equivalence per unit volume in liter, and it has the symbol capital N. The reason why acids and bases are always in a one-to-one equivalent ratio is because of what we mean by an equivalent. An equivalent, let me annotate this real quick. An equivalent for acid is H+, which we can write as H3O+. An equivalent for base is OH-, and these always react in a one-to-one ratio. By definition. So it doesn't matter what the source of acid or base is, they contribute one equivalent of either H3O+ if you're an acid or OH- if you're a base. Now, what's not always in a one-to-one equivalent is the moles per equivalent. That can change. So for example, if I have a monoprotic acid like HCl, 1 mole of HCl gives me one equivalent, H, yes. But if I take something like a diprotic acid, oxalic acid, 1 mole of H2C2O4 gives me 2 H's. So that would be 2 equivalents in a mole. If I take a triprotic acid like phosphoric acid, then 1 mole of phosphoric acid gives me 3 moles of H. So the equivalents are always one-to-one, but the equivalents to moles can vary depending on the polyprotic nature of the acid. Okay, so we've got normalities. We can now perform titrations. We perform titrations in a burette, which is essentially a long, thin tube. It looks like a graduated cylinder, but it has a tap or a stopcock at the end, and we can accurately dispense volumes, typically to 2 decimal places. So for example, if we're asked to, we have a scenario here, 34.5 milliliters of arsenic acid was titrated with a given concentration of magnesium hydroxide. The initial burette reading of base was 1.48 milliliters, and the final reading was 40.24 milliliters. What's the normality of the acid? Okay, well, we can look at the total volume of base titrated. The total volume of base titrated is the final volume of the base minus the initial, which is 40.24 mil minus the initial value of 1.48, which gives us 38.76 milliliters of base. If we construct the calculation backwards, we know that we have equivalence of base. We know that by definition, 1 equivalent of acid is equal to 1 equivalent of base. So hopefully you can see my marker circling around here, and my annotation laser pointer circling around here. So by definition, 1 equivalent is 1 equivalent. Here we've called them milli equivalents, just so we don't have to convert to liters. We can just use our milliliters so long as we use milli equivalent. But you can use liter and equivalents as well. It doesn't matter. So we have a milli equivalent of each. Then my denominator milli equivalents of base becomes the preceding numerator. I know that 2 milli equivalents of base is 1 millimole of base. That's because if I take magnesium hydroxide, I have 2 hydroxides in 1 magnesium hydroxide. Hence, I have this 2 milli equivalents to 1 millimole ratio. My millimole denominator becomes a preceding numerator. And this input is the definition of molarity. So I have 0.1049 moles of magnesium hydroxide equal to a liter, or that many millimoles equal to a milliliter. And then my denominator, milliliter, precedes now as my input volume. And my input volume is the volume that I titrated. So far, everything gives me my numerator, milliequivalents. Finally, I need my denominator, how much original acid I had, and I had 34.5 milliliter. Putting this in as an input at the end, I now have a calculation, and it gives me 0.235705 milliequivalents per milliliter, or equivalents per liter, depending on how you want to phrase it. Either way, I say I have a 0.2357 normality solution. Okay, and the final slide for these would be, instead of an acid-base titration, we can have a redox titration. So we can do the same again, but we can have, for example, ethane in the gaseous form. So this is a combustion reaction, which is also redox. We can have ethane and oxygen to give CO2 and water. Let's assign oxidation states to everything. So by definition, the element oxygen is just 0. Water, we have a neutral compound, and we have preferential -2 charge on oxygen and 2 positive charges on hydrogen, which sum together to give a neutral compound. CO2, again, we have a preferential charge of -2 on oxygen. We have 2 of those, that's -4. So we need a +4 charge on carbon to offset that -4 charge on the oxygens. And finally, we have a preferential +1 charge on hydrogen in ethane. We have 6 of those, that's +6. So that means each carbon must have a -3 charge to offset the +6 charge on the hydrogens. So in short, the red digits give you the assigned oxidation states for each element in this combustion reaction. Remember from a previous slide, we said that the oxidizing agent undergoes reduction. So here we have oxygen going from the 0 oxidation state on the left to exclusively the -2 oxidation state on the right. We've decreased our oxidation state from 0 to -2, which means we've added electrons or we've gained electrons. So remember the acronym oil rig, reduction is gain of electrons. That's what's happened here to oxygen. So oxygen underwent reduction. So therefore, oxygen is the oxidizing agent. And we always refer back to the original chemical when we label the agent. Hydrogen does not change oxidation state. It stays as the +1 oxidation state throughout, so we can ignore it. Carbon, on the other hand, changes on the left from the -3 oxidation state to, on the right, the +4 oxidation state. This is a gain in oxidation state. It means that we are producing electrons. We are increasing our oxidation state. We're producing electrons. Therefore, because of the acronym oil rig, we've lost electrons from the reactant. We've produced them as a product. Therefore, the carbon is undergoing oxidation. Therefore, we look at the entire chemical that contains the carbon, which is the entire chemical ethane, and we label that the reducing agent. And that concludes this video.